turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists podcast, the programme that brings you the biggest breakthroughs and talks to the major movers and shakers in the worlds of science, technology and medicine. With me, Chris Smith. On the way, doctors operate to fix a developing baby still inside the womb. So how did they do it? Also, the crafty tricks that gambling machines use to take the sting out of losing and make you bet big. And lunar littering or a fortuitous space crash? Why a chunk of SpaceX rockets slamming into the moon might actually help to unlock the history of previous impacts and craters. First this week, a team of doctors have used groundbreaking surgery on an unborn baby to successfully correct a birth defect called gastroschisis while he was still inside the womb. The baby's mum, Maisie Savage, who's from London, was operated on by doctors in the US while she was 26 weeks pregnant. Sandeep Keswani and his team at Texas Children's Hospital performed the operation.
Gastroschisis is the most common congenital abdominal wall abnormality. It's when babies are born with their intestines outside of their body. It's actually a normal part of development, and it just doesn't happen in these kids where the intestines, and say you and I were outside, and now they don't go back in these kids.
So the abdominal contents would normally develop outside the body. They retreat early on in development. And in this case, that closure had not happened. So all the intestines and things, this is the baby inside mum, were still outside and they shouldn't have been.
That is absolutely right. But it's not necessarily that fact, the defect, because surgeons can close that. The problem is that by the time that the baby is delivered, the intestines don't work. Those babies stay on for 3 to 6 months in the NICU. They go on to feeding difficulties till they're 4 or 5 years old. And then they also can go on to intestinal transplant, and even 1 in 10 babies die in the US. So in good children's hospitals, the outcome still isn't great.
And how have you sought to intervene?
We're trying to get to the baby, to the problem before it becomes a real problem. And so in the middle of gestation, around 26 weeks, the goal is to go into the mother using this keyhole surgery and put the bowel back into the baby, basically anatomically correcting it the way we do it postnatally, but doing it in the middle of gestation or during the pregnancy so that the baby can then recover for the next, hopefully, 13 to 14 weeks before the baby is then eventually delivered.
How on earth do you do that? Because if we think about the anatomy, you've got the mum's abdomen, and inside her pelvis is her uterus, the womb, and inside there is a bag of fluid made by the baby with a baby inside it. So you've got to operate through the abdominal wall of the mum, the wall of the uterus, the bag of fluid the baby's in, and then into the baby.
Well, when you put it like that, you make it sound so hard. Now, it is to do that, to make it through all of that. First, in transparency, we actually open the mother's abdomen so that we can see the uterus. And the uterus at 26 weeks is above the level of the belly button. So it's there in your plain sight of view. But now what the difference is and the advances, instead of making a large incision on the uterus to get to the baby, what we do is we use little, almost like straws, and we put these laparoscopic instrumentation in to then be able to access the baby. We then take out that fluid that she mentioned and we instill air instead, so it's carbon dioxide. And so we insufflate this uterus, and the uterus is relaxed, so it becomes like a balloon and it gives you an operative field. And now you're looking at the baby, and what we do is we slowly and very gently push the intestines back into where the umbilicus is. Now, the one thing you didn't mention was the umbilical cord, because you still need that, because that's where all the blood supply comes from the mother to the baby. So we now have to stitch and close this defect at the same time making sure that we don't hit those or injure those vessels that are critical, essential to this baby's life. And then we close the defect, and then we put the amniotic fluid back in, we take our ports out, close the mother, and then hopefully she goes on for the rest of her pregnancy.
Is it easy to spot the umbilical cord and tell it apart from the developing
Yes.
intestines?
Absolutely. It looks very, very different. It's like the size of a fettuccine, and the defect that we're pushing it in is the size of, say, an eraser head. And so you're slowly pushing this very overcooked fettuccine because it's very, very soft. And the umbilical cord, on the other hand, is almost more like a rope-like structure because it has the 2 arteries and the vein in it. And so you can clearly see what that is. It has a very different texture, a very different look.
How big is a 26-week gestation baby?
About 600 grams, usually between 5 and 700 grams.
So is that sort of slightly bigger than a human
Oh,
hand?
sorry. Yeah, exactly. The size of a human hand.
And are those intestines not incredibly fragile? Because I'm just thinking you've got your instruments, these little, you put it very well, as straws going in there. Is this not like trying to eat a bowl of fettuccine with chopsticks? How on earth do you manipulate them and get them back in that tiny hole to fix everything?
Well, one, I would say there are probably many people listening to this show today that think that they could eat fettuccine with chopsticks. So that comes with practice, and it comes with understanding the structure, the biomechanical strength, so to say, of that fettuccine. And so the way we did that is we actually worked with bioengineers and developed 3D printed models of what this was going to look like. And we did biomechanical testing on these polymers that we had made the intestines out of. This is like obviously a practice model before we do it. So we've gotten some pretty good tactile feedback from our 3D printed models to be able to tell us what we're doing is right. And I will tell you, it's pretty accurate. When I've done it now in humans and in real form, it's very much like the simulator.
And when you get the intestines back where they should be, do you close up? Because they're wrapped up inside the individual, aren't they? So do you close that up when you close the baby's abdominal wall up then? And then are they destined to work properly thereafter if you do this?
One of the features of gastroschisis is there is no sac. When there is a sac, it's called an omphalocele. That is a much larger defect and probably not amenable to a surgery like this, at least not yet. However, when you do put the bowels back in, there is the peritoneum in the skin, which the peritoneum is that inner lining of the abdominal cavity. We just close the skin itself and bring it together. I think the question, the last question that you asked is really the important one. Is this going to work? And no matter how much modeling over the last 10 years that we had done, you never were going to know until you actually did it. Because there is no animal model, there's no 3D printed model, there's no clinical experiment that you could do to actually tell you that this was going to restore intestinal function. And when we took this to the US government, the FDA that's approved this study, they agreed with that. They said there's just nothing else you can do until you now do it in humans. And that's where we are. And what we've seen in the 3 patients that we've done is that indeed it does. Indeed it does. It causes the intestines to function normally at birth, at least has that potential. And certainly in this last patient that we did, the last 2 that we've done, the babies come out of the womb and they start feeding right away, just like a normal baby. They're on gold feeds by 2 days. And they're going home at 3 or 4 days, just like any other normal baby, with their intestines working.
It's a great story, isn't it? Although I shall never look at a bowl of fettuccine in the same way again. That was surgeon Sandeep Keswani at the Texas Children's Hospital. Astronomers have warned about the long-term effects of space debris after a huge abandoned rocket part hit the moon this week. SpaceX's Falcon 9 rocket was launched last year. Its upper section, which weighs 4,000 kilograms, was shed into space as planned, but deviated onto an accidental collision course with the lunar surface. Thankfully, it didn't wipe out Neil Armstrong's iconic footprints, but an impact of the future might, and that is why we need to be careful what we do up there. Nevertheless, impacts like this do have a silver lining because it can help to unpick the anatomy of previous natural collisions and what caused them. Here's space scientist Megan Argo with the intel.
So this is a rocket body that's been in a high orbit around an elliptical high orbit around the Earth and the Moon since early 2025. Its original aim was as part of a mission to take 2 lander spacecraft to the moon. So this was a SpaceX Falcon 9 rocket that took off in January 2025. It's a 2-stage rocket, so the lower stage of the rocket, the main core stage of the rocket, is the bit that gets you from the launch pad into low Earth orbit, and that part of the rocket is reusable. So that stage, once it had done its job and taken the upper stage and the landers into low Earth orbit, it returned to the ground, landed on one of SpaceX's barges, and has been refurbished for reuse. The upper stage of the rocket is the bit that takes the spacecraft off to the moon. That requires an extra injection of energy to get you out of Earth's orbit and off towards the moon. Once it had done its job, which it did successfully, then it was no longer useful. So it separated from the spacecraft, sent them on their way. They went off and landed on the moon's surface. And it was left basically just in whatever orbit it was in at the time when it separated from the spacecraft. Now, ever since, it's been in this elliptical orbit, and the combined effects of the gravitational pull from the Earth, the gravitational pull from the Moon, and the slight pressure, the slight radiation pressure that you get from sunlight, has conspired to alter the orbit of this rocket body until yesterday morning it hit the Moon's surface and created a brand new crater.
How fast was it going and how much does it weigh? So, in other words, how much energy would it have had when it slammed into the Moon?
So it weighed, we think, about 4,000 kilograms. Its exact mass is not 100% known because we don't know exactly how much unspent fuel was left on board. So that will have affected its mass and its dynamics slightly. In terms of its velocity, it would have been traveling a couple of kilometers per second, which sounds fast, but compared to the rocks that normally hit the Moon's surface, that's actually a pretty slow collision.
What's that, about
So it's different to the
6,000
normal.
miles an hour, something like that?
Yeah, that kind of order of magnitude, yes. So it's fast by everyday standards, but still slow compared to most of the rocky debris that's floating around the solar system that hits the Moon on a daily basis.
The SI unit of how hard things hit things is usually expressed in tons of TNT, isn't it? So have we got a TNT equivalent for this?
Oh, there is, but I'm not sure what it is, actually.
It must be
I'd have to
quite
go look
big.
it up.
But when it slams into the Moon's surface then, I mean, is this just littering on a cosmological scale and really naughty? Or does this serve a scientific purpose? Can we actually use this, now this has happened, to further science?
It's space junk, it's debris that, in an ideal world, would not have accidentally landed on the Moon's surface, would have been put in a safe orbit that would have kept it well away from anything important. But as it has impacted on the Moon, and it was predicted months in advance it was going to impact on the Moon's surface, where it was going to impact and the time it was going to impact. There was lots of opportunity for observatories around the world to decide how they were going to observe it. And the first data that I've seen from it, I haven't yet seen images, although a lot of people were trying to get images of the impact. There was a lot of uncertainty as to whether there would be an impact flash. We know impact flashes happen on the Moon's surface again on a regular basis. The Artemis 2 astronauts earlier this year, they saw impact flashes when they were around the far side of the Moon's surface, in the side of the Moon that's in shadow from the sun. And these are when rocks that are flying around the solar system at, much higher velocities impact the Moon's surface. Part of that energy is converted into light, and you see an impact flash. And again, from the Earth, we see those impact flashes as well on the parts of the Moon's surface that are in darkness. This would have been a less bright impact anyway, but the impact also happened on a part of the Moon's surface that was in full daylight. In fact, it was almost noon, I think, at the position where the impact occurred. So the chances of us actually seeing the impact flash were pretty slim. But what did happen was a lot of material was kicked up in this impact. So a new crater was formed, which we will hopefully get images of from Lunar Reconnaissance Orbiter sometime in the next few days, which has got obviously lots of images of the location taken before the impact, because it's been in orbit around the Moon since 2009, imaging the surface. So we'll get after images, hopefully in the next few days, where we'll see the exact size of and shape of the crater that's been formed here. But all the material that was kicked up from the surface, lots of rocky debris, was sent, some of it many kilometers into space from the Moon's surface. And that plume of material was also being imaged from the Earth as well. So observatories that were in darkness at the time, so places in the Americas, had darkness at the time, so we're in the best position to try and image this plume. And the first data that we've seen comes from the European Southern Observatory. So one of their telescopes at Paranal actually took spectra of the Moon before and during the collision and just after the collision. And what they've seen in their spectra is evidence of sodium and lithium lines, emission lines, that were not there prior to the impact. So what they think is that the sodium was from the lunar debris itself, from the material from the rocks that were kicked up in the explosion, and the lithium is from the rocket body itself. So lithium is a common constituent of batteries, for example. So plenty of heavy metals involved in that rocket body. So that's the first data that I've seen. And the interesting thing about all of this information is the images and the spectra is it helps us understand these impacts on the Moon's surface. We know that rock hits the Moon's surface on a daily basis, but what we don't know in advance is the size and velocity of those rocks doing the impacting. So we can see the craters that are formed, but we don't know much about the impactors that cause them. Here, we know the properties of the rocket to a high degree of precision. So we know its size, its shape, its mass to within, a few hundred kilograms. And we know its trajectory. So we know its velocity and we know that it was tumbling as well. So we know the impact parameters. So by comparing the properties of the crater that we see with the properties of the impactor here, we can use that to help us understand better some of the other impacts that we see on the moon's surface.
So you can sort of post-mortem the other craters and backtrack on their history, what must have caused them, and if we know roughly how old they are, that tells us what sorts of things must have been floating around on a moon impacting course at that point in history.
Yes, exactly. It helps us validate some of those models so that we have seismometers on the moon. So this was a common thing during the Apollo days as well. Apollo missions that landed left behind seismometers that were active on the moon's surface for many years after the Apollo missions ended. And they were registering moonquakes from the regular impacts that happened. In fact, some of the Apollo rocket bodies also impacted the moon deliberately to provide data on those seismometers as well. So a lot of modeling has been done about impacts on the lunar surface and the differences between impacts that land in rocky regions where you're actually landing on bedrock and other regions where you're landing in deep regolith, that lunar soil, that fine dust, which can be many, many meters deep in places. But validating those models requires us to have impacts like this one when we know what the properties of the impactor are in the first place and can compare that data with what we see on the ground.
It's amazing what you can learn from a clapped-out lump of old rocket, isn't it? That was Megan Argo there.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
This is the Naked Scientist podcast with me, Chris Smith. Now, we're halfway through today's programme, so I wanted to share some of the other great content that we publish each month, like our Naked Astronomy podcast strand, which is put together by the fantastic Space Boffins. If you're interested in space science stories, then do give that a look and listen. It's at nakedscientist.com/astronomy, or just look up Naked Astronomy wherever you get your podcasts. Now, anyone who's ever been to a slot machine arcade knows that these places are an audio-visual extravaganza. There's lots of bright, colourful, flashing and blinking lights, coupled with exciting sounds and usually a thudding drumbeat-led music. Now, this is all designed to draw you in and persuade you to part with your money. And in that, it seems to be a very successful strategy. Brett Hathaway at NIH has found that rats can be encouraged to make much riskier high stakes, but ultimately higher loss rate decisions when the wins are associated with rich light and sound stimuli. But it isn't that the sounds and lights reinforce the winning. Surprisingly, the effect seems to be working by making the losses less painful.
We were really interested in understanding cognitive processes that underlie a key effect that we found, that adding salient lights and sounds to a risky decision-making task in rats increases their risky choice.
I mean, adding sound and light, Brett, it makes it sound like gambling machines.
Yes, that's exactly correct. We know from the human research that there's something about these electronic gaming machines or slot machines that are really increase the state of immersion and can be particularly challenging for those with gambling disorder. So we're really trying to understand, what is the effect? Of course, we all know that these machines have tons of sensory stimulation going on. So what exactly is the effect of that on the decision-making process?
How did you test it? What did you do with the rats?
We use 6 different variants of this rat gambling task. So on this task, there's 4 different options they can choose from. 2 of them are low risk, low reward. So they actually maximize the ability to earn sugar pellets over time, versus the 2 other options are high risk, high reward. So they win more on a single trial, but they're more likely to lose. And when they lose, they go into this long timeout penalty. So they actually lose out on the maximum number of sugar pellets that they can earn.
And if you compare all of those tasks side by side, you're saying that the low risk ones actually, if played consistently, would lead to a bigger reward than if you take the higher risk. Although you're occasionally going to get more lucky, overall you're less lucky because the reward total is lower.
That's exactly right.
And so for a gambler with a gambling problem, or a company running a gambling arcade, they want the gambler to take the high risk option, low reward for them, high reward for the person running the gambling machine. the gambler's ideal choice would be the lower risk option.
Yeah, so the designers of these machines are trying to obviously maximize their own wins. So they want people to getting that balance between keeping people engaged and, essentially thinking they're winning, whereas in reality, it's the slot machine companies that are winning out overall.
So just played normally then, what do the rats do?
Without any win-associated cues in the task, they actually are able to determine that these low risk, low reward options are better, and they maximize their choice of those options. They'll still sample the other ones a little bit, but overall, the majority of the time, they're going to choose these low risk, low reward options. They don't have much trouble figuring that out in the uncued version of the task.
So then what did you change?
We have a version of the task where we add win-associated cues. So this is across all 4 options. Any trial that they have a winning outcome and get those sugar pellets, there's a light and sound compound cue that is going to be played. In the standard version, these cues scale in length and complexity with reward size. So the low risk, low reward options have just 1 or 2 tones and 1 or 2 lights that flash, whereas the high risk options, when they get that bigger reward, there's sort of a 7 to 8 tone that varies in complexity across trials that will play. And so we know that that version can result in a higher number of rats going for those risky options.
When you make the rats get a really rich win like that with lots of stimulation, all those sounds and lights, and it's very dense and complex, that reinforces the choice they made. So if it was a high risk choice and they got a massive great win, it pushes them towards doing that again.
That was kind of the hypothesis that we had before we did this current study, that because the cues are on the wins, it must be something about getting this really rich sensory information on the wins is going to, overemphasize those, and that results in repeating that choice. But actually from this study, it looks like it somehow changes the processes of the losses. They actually aren't able to integrate that information into the sort of value of that option. And so that is what's driving them to repeat that choice.
That's really interesting, isn't it? Because we've all thought that it's the dopamine and adrenaline rush of the win, but you're saying it blunts the sting of the loss.
Yes, exactly. And that's true. So in this study, we also included a version in which we cued both the losses and the wins, and we still got the risk-inducing effect. And we still saw that effect where they aren't attending to or able to integrate those losses.
Yeah, what led you to that conclusion? Because I can see how the experiment leads you to the conclusion, well, we reinforce a risky decision with all these extra stimulations when they win, and that would encourage them to do it more. But I don't see how you were led to conclude that the losses are less painful.
We used a method called computational modeling to basically come up with algorithms that should somehow represent the underlying cognitive process that the rats are using to come to these decisions. And we were able to use this technique to show that, we can produce data just from that model that matches what the rats do. And we were able to see that we had 2 different learning rates. So we had a learning rate for rewards, which is essentially when you get a winning outcome, how much is that going to update how much you value that option? And so we split out that learning rate for rewards and punishments. And we found that across these different tasks, having any version of a task where wins are associated with cues, that seems to decrease punishment learning rate. So they're not learning as much from those losses.
Does the same apply in humans? So if you look at our behaviour when we're addicted to gambling, or we tend to go into a gambling situation, do humans seem to do what the rats do? And therefore, do you think the same cognitive mechanism is at play?
So we have a couple lines of evidence that suggest that is the case. Someone else in the lab translated this task into humans and looked at the effect of win-associated cues, and we actually did replicate the effect in humans. I think the most sort of direct application of this to what goes on in a slot machine is this idea of losses disguised as wins, which is essentially where they play a win-associated cue. You've won some amount of money, but you haven't won as much as you bid in the first place. So it's actually a loss, but they play these sounds and lights as if you've actually won. And that seems to be a real driver of both gambling disorder and increasing the length of play, and actually alters your perception of how much you think you've won and lost. So I think that's some indication that these same processes are going on in humans, and particularly in gambling disorder.
Really interesting that, isn't it? Brett Hathaway from our eLife series of podcasts. You can get more from that at nakedscientist.com/eLife, or look up the eLife podcast wherever you get your podcasts. Holidaymakers in the US and Europe have been warned about a recent surge in cases of a foodborne intestinal parasitic infection called cyclosporiasis, which causes extremely unpleasant, prolonged bouts of explosive diarrhea. Apologies to anyone eating right now. An outbreak in the United States has infected tens of thousands of people across most of the country's states, and 2 people with underlying health conditions have also died from it. The culprit appears to be Mexican lettuce, which has somehow become contaminated with the parasite, presumably from a sewage source. Lisa Kachara is a biomedical scientist at Quinnipiac University, and she's just penned a piece about the outbreak for The Conversation.
So this particular agent is a parasite, and it is something that is spread only through human feces. It is something because somehow or another, somebody probably did not wash their hands and it has gotten into our food processing system.
The only host then is a human.
Correct.
And where are we having problems with it at the moment?
So we're seeing cases of this particular cyclospore parasite in the UK, in over 35 states in the United States. So it is indicating that there is something that is of a global scale.
What do we think the source is? As in, when scientists and medical epidemiologists see this kind of thing happening, they usually go after the source. So what do we think that might be?
So going after the source seems easy, right? Like we just track something back. But what did you eat 3 weeks ago? It becomes something that becomes a little harder to be able to kind of pinpoint the exact source. For this particular outbreak, the source has been linked to lettuce, especially lettuce that's kind of more mass produced, going out to restaurants, going out to fast food chains, going out to supermarkets. Not likely your local produce, because that is something that kind of has an internal level of possibility of contamination. Outbreaks in the past of cyclospora have been lettuce, raspberry, spinach, cilantro, basil, but it's really taken a while for the epidemiologists to kind of figure it out. It's a very lengthy 7-page questionnaire that you ask somebody that has self-identified with kind of having this explosive diarrhea, and then you're trying to figure out what is the pathogen, what's the germ that's actually causing this, and then what is the commonality of people, what did they actually eat. So it takes a while. Like, do you remember what you ate 3 days ago, let alone, a week ago or 3 weeks ago? So it takes a long time in these types of situations to be able to kind of track back the source.
Lettuce doesn't catch this parasite, so it must be on the lettuce. So it's sewage
Correct.
getting onto the lettuce. So where's the lettuce coming from?
So it appears this particular outbreak of lettuce is coming from Mexico, and it's being distributed widely. So it is something that could be under multiple labels, going to multiple restaurants, going to multiple fast food chains.
Yeah, do we know what the contamination route is? Is it because, for instance, people are using sewage on fields as fertiliser? Or is it something else that's introducing the parasite onto the lettuce?
It's unlikely that we're using human sewage as fertilizer, but sometimes what happens is water levels might rise after a certain flood. Something might happen where then that sewage kind of contaminates perhaps the water that is being used to, irrigate the crops. It could be actually contaminating the water source that's used to clean the lettuce. So here you're trying to clean the lettuce, and you could actually be introducing the pathogen during that process as well.
What's the infectious dose? So a person eats some lettuce. How much of this parasite do you have to consume to be likely to pick it up?
Right. So there are certain germs where if you get exposed to 10 of them, you could get sick. So norovirus is one that you have a very low amount of germs that can make you sick. Something like salmonella, you need millions of them to make you sick. This falls in between there. So there's no exact number. And we know that rinsing our lettuce is going to help decrease the amount on there. Although lettuce is kind of bumpy, it's got little tiny hairs. So the eggs actually stick very well to lettuce. So it's kind of hard to rinse it thoroughly. If you are buying a head of lettuce, removing the outer leaves and then rinsing your remaining leaves thoroughly will decrease your chances of getting it.
So if you have a person who catches this and they're symptomatic, can they give it to other people?
So you really can't have human-to-human transmission of this particular parasite. So that's the good news. So if you're cleaning up after somebody that has it, if you were in a hotel room after somebody that had it, if you're in any kind of public environment or family environment, you're not likely to catch it human to human.
And how long after being exposed will you know you're in the clear?
Ooh, that's a good question. So generally, when you eat this, within 4 to 8 days is when you start showing symptoms. Because again, who remembers what they ate 4 days ago or 8 days ago? So I would say if a week has gone by and you had a wonderful salad and you went, "Ooh, I didn't really realize I shouldn't," you're probably past the clear. On the other end, though, if you get infected, you could have this last 3 or 4 weeks, and in some people, it even kind of seems to reduce and then kind of re-flare up again. So a lot of people talk about germs and say, oh, our society's too germophobic. It's okay to get sick. Most people don't want explosive diarrhea for 3 to 4 weeks. I think that's a pretty commonality among most humans on our planet.
What should people do about it then? If they develop the symptoms, they've got a track record. They were in the affected geography. Perhaps they were on holiday in America, or perhaps they've come back from somewhere else where there's been activity. They get this diagnosis. What can they expect and what can we do about it?
So definitely, I think this is an underreported disease because most of the time, if somebody has diarrhea, they don't necessarily seek out their doctor. They kind of might search something up on the internet, and they might go, "Well, I might have to buy some Pedialyte." But in this particular case of an outbreak, if you're exhibiting explosive diarrhea, so when you have that as a symptom, definitely go to your local doctor, get tested. There is an antibiotic in this case that actually disrupts this parasite. I think the biggest thing for people to be aware of is it's easy to get dehydrated. So that's what can end up people in the hospital is that now, you really are going through these symptoms and you're not realizing how quickly you can get dehydrated, how quickly your electrolytes can get out of whack.
Nasty business, so maybe skip the salad for the time being. Hopefully, though, those cases are going to stop cropping up soon now that we know the cause. Lisa Kachara there, she's at Quinnipiac University. Now that's it for today. Do tune in on Tuesday though, when we're going to be previewing the solar eclipse, which is taking place in Europe. It will be the best chance to view one for a very long time. Not for another 80 or 90 years actually, and we'll tell you all you need to know about it. Meanwhile, if you'd like to get in touch with us, you can drop us a line to chris@thenakedscientist.com. We very much welcome your thoughts, comments and feedback. And if you like what we do for you each week and you would like to support us, we would really appreciate that too. nakedscientist.com/donate is the address to head to. And we are really appreciative of anything you can do to help us keep the show on the road. I'm Chris Smith, and from all of us here at the Naked Scientist team, thank you for listening. Have a lovely weekend, and until next time, goodbye.